Okay, good afternoon, everyone. So today is the fifth interaction session on structural vibration. My name is 𝜷. I'm a research scholar and primary studies fellow at IIT Guwahati. So for this semester, I have been allocated to this course. Every week on Saturday from 3 to 5 p.m. we generally meet, and what we do during this 2 hours interaction session. So first we go through the concepts of the current week, and then we solve assignments on pen and paper which are useful for your current week assignments, and then we solve different kind of problems during using the MATLAB. Okay, so today we will go through the numerical solutions of dynamic responses, how we can get the numerical solutions, what are the different methods to get the numerical solutions, and what are the criterias, different criterias, and all these things for that. Okay, so I believe I am audible, and my slides are also visible, right? Okay. So today, first we will talk about different kind of numerical techniques to get the dynamic responses. So first we will go through the Nigam Jennings method, and then we will move to central difference, and subsequently we will go through Newmark-𝜷 and Wilson theta method. Okay, so let's start quickly today's session. So one second. Okay, so during few weeks, what we have gone through, the different you know mm, force and free vibrations of different dynamic systems, where first we have formulate the equation of motion, right? And uh, sorry, actually I am facing the internet problem. One second, I need to fix it first. Yeah. Okay, so we have solved different problems of free and force vibration, where we first formulate the equation of motion, mx double dot plus cx dot plus kx equals to some forcing function f, or f of t, right? And then we have solved mathematically for the responses at different time step, like x of t, how we can get the x of t and different responses at different time. So till now we haven't talked about any numerical techniques which we can use to get the solutions directly. So first, like we have solved this problem, we have solved for different kind of loading, like f of t we have used harmonic loading. Yeah, here we have used harmonic loading. We used a different kind of step and pulse forces to get the responses, and also we have seen that how we can get these responses correctly. Okay, so okay, am I audible? Can you someone confirm? Like I am facing some internet issue here, so am I audible? Can someone confirm? Nadal? Okay, great. So we will first go through that Nigam's and Jennings method. First, we will see the concepts behind it, and then we will move to the MATLAB portion where we will solve different kind of MATLAB. We will code it first, and then we will solve different kind of systems using it. Okay. So first, like we need to start with the equilibrium equation at time instant. One sec. Yeah. So we have started with our um, you know with the equilibrium equation mx double dot plus cx dot plus kx is equals to f. Now, if we have a arbitrary loading here, you can see uh, any general arbitrary loading, and if we can assume that for two time points, say for instance ti and ti plus 1, so we have two time instances. So for these two time instances, if like 1 second, it's still getting problem. Let me share it again. Yeah, now I think it will help to uh, do it properly. Okay, so we start with our general assumptions, and if we can consider that my load is linearly varying, then we can express the function, that loading function f of tau is equals to f of I plus, yeah, f of I plus del fi plus del ti. Another, can you please mute yourself? Yeah, thank you. You need, I'm facing little internet issue, but still I will try to cover how we'll go through it. Okay. So the forcing function here can be expressed in terms of this: f tau is equals to fi plus del fi by del ti multiplied by tau. Now, obviously, that del fi is nothing but the difference between that two time instant ti and ti plus 1. So if we substitute this forcing function here, and for the simplicity for now, but when we will go through the MATLAB examples, then I will show you that how we can incorporate the damping also, the full term of damping. So here for now, consider that no damping is present. So the equation of motion looks like this: mx double dot plus kx is equals to f of tau here, and instead of f of tau, we have already defined our forcing functions. Like, the forcing function is nothing but that fi plus del fi. Now the total response we have already seen when we have solved different uh, uh, with different damped force vibration case. We have seen that our total response depends upon two quantities. First one is the free vibration case, and then due to the constant force or due to different kind of forces whichever acting on the system, and third part due to the ramped force. Okay, so now here for these three systems, if we solve on the right hand side, you can see that first, this one is nothing but the forcing function due to, or the response due to the free vibration case. Then the second one is the response due to the constant force, and the third one is the response due to the ramped force. Okay, so tau here nothing but, what is tau here? Tau here is nothing but the time interval between 0 to t, the time interval between 0 to t. So for this condition, if we again look for the solutions, then what we will get here, like total x tau will be nothing but xi, the initial condition, cos omega n t plus x dot I, that means the initial conditions, into sin omega n tau, because this part is nothing but my free vibration part. Okay, already you have solved for the free vibration part, and then we have the constant force term, which is represented by fi by k, 1 minus cos omega n t, plus we have some forcing function over here, which is represented by del fi by k, that is the due to the ramp force. Now this is what that actually implies. That implies the response at tau for the that we have assumed that the force is varying linearly and the linear interpolation for the force is possible. Now if we put if we differentiate with respect to tau, what we will get? Obviously we will get the velocity. And if again if we put t is equals to tau on the previous slide, if we go to the previous slide and look for this thing, so we can see that uh, if the del tau is nothing but the time difference between that two time instant, initial and the final point. And if we proceed with that, what we will get? We will get the solutions of at t I plus 1 point. Okay, so the total solutions x I plus 1 will nothing but that xi cos omega n del t plus xi dot by omega n sin omega n del t plus fi by k, 1 minus cos omega n del t plus del fi by k, and these things and so on. So if we simplify these equations, so what we will get in a combined form, we will get here in the uh, boxes over there, red marks boxes over there. So we get the responses at xi plus 1 time step. That means the responses at the next time step, and which actually denoted by nothing but axi. A is nothing but, here you can see the term. So when we will solve using MATLAB, I will show you that how we can get these responses with that. And then B xi plus c fi and d fi plus 1, because the forcing function at fi and fi plus 1 both we have considered for here, and then we have solved for it. Okay, so basically it's a straightforward equation, and Nigam and Jennings, two engineers, actually have proposed this method. That's why we call this method as Nigam and Jennings method. And further, if we move, then what we will see that how to solve this kind of problems easily. So on the next slide here, one example I have put it here, that how actually using that Nigams and Jennings method, how we can solve for a dynamic response for different time instances. So here from these two equations we can see that xi plus 1, that means the displacement at the next time step I plus 1 is nothing but some constant term into xi plus b xi dot plus c fi and dfi. So a b c d, these are the constant term here. If you simplify these equations, you can see that which terms actually correspond that a b and c d. And for that velocity term, we have used that a prime, b prime, c prime and d prime. So to solve any kind of system, what we need to have, we need to have the uh, the displacement at ith point, the velocity at ith point, and the forcing function at ith point and I plus 1 point. So if we can solve that a b c d and a prime, b prime, c prime and d prime, we can easily solve the responses at time instant I and at time instant I plus 1. So here for this example, if we go through this example, what this example says, an external force Ft, the force is given here, Ft is nothing but 15 sin 3t kilonewton, is acting on an SDF system. Initial displacement and initial velocities are given. It's starting from the complete rest position. That means both initial displacement and initial velocities are 0. Now calculate the displacement x of t and velocity at t is equals to 0.1 second, considering the time step also given 0.1 second using the Nigam's and Jennings method. The calculated constant values, like whatever we have seen here, to get the responses at I plus 1, we need to calculate the a b c d values, and a b c d and a prime b prime c prime d prime is actually contain the information about the system, like omega n, what is the del t, and all of these things, what is the forcing function, and all of these things. So here the forcing function is also given the in terms of a sinusoidal force whose amplitude is given as 15 sine 3t. So according to Nigam's and Jennings method, the displacement at time t is equals to ti plus 1 is nothing but xi plus 1 is equals to axi plus bxi dot plus cfi and dfi plus 1. That means we need to calculate the force at if I is equals to 0 and if I plus 1, that means the next time point where we need to calculate the force. So here we need to calculate the response at 0.1 second. That means first we need to calculate the force at 0.1 second. So what will be the force at 0? Obviously 0. What will be the force at 0.1 second? So here the forcing function is given 15 sine 3t. So instead of t, just replace 0.1. So we will have 4.433 kilonewton here. And for other time instance also, if we need to calculate the response as 0.2 seconds, then we need to again calculate the force at 0.2 second, and we will have some forcing function over here. Now, what we need to do? We need to calculate the displacement at 0.1 second. Look here, A, B, C, D and A prime, B prime, C prime, D prime already have been calculated and given in the question. So displacement at t is equals to 0.1 second. What was the formula? It's nothing but A, that means the constant value already given 0.99 into xi, that means the initial position or the initial or the starting position of the system. That means a x naught, the initial conditions are given as 0. Now b, look at the b value is already given 9.9 into 10 to the power minus 3, and the x dot naught, that means the initial velocity, and already the initial velocity is provided as 0, plus c into f naught. So at t is equals to 0, obviously sine 0 means 0, so f 0 obviously 0, so only we will left with the last term d into f of 1. So that value of d is already given here, 1.66 into 10 to the power minus 7, multiplied by the force at t is equals to 1 second, already have been calculated as 4.433 kilonewton. Now if we calculate it, we will get the displacement at t is equals to 0.1 second. So that comes as 0.74 mm. Subsequently, if I need to calculate the displacement at t is equals to 0.2 second, what we need to do? So then the initial condition will become that t is equals to 0.1 second. What is my displacement? What is my velocity? What is my forcing function? And then we need to calculate the a, b, c, d, a prime, b prime, c prime, d prime, and subsequently we will get the displacement and velocity at t is equals to 0.1 second and t is equals to subsequent sections. So displacement we are already calculated. Now how we can calculate the velocity? Recall the velocity. For the velocity here, the equation is straightforward. A prime, that means that constant, that term actually contain the natural information about the system. So already a prime, b prime, c prime and d prime are given here in your question already. So what we need to do? We just need to calculate straight away, because at forcing function at zero point 0.1 second we have already calculated, and that comes as 4.433 kilonewton. So velocity at t is equals to 1 second, it comes as 0.22, because only the last term d prime into f naught will be there. So if we consider and calculate all of them, we generally get the velocity also at t is equals to 0.1 second. For now, like any time point, if other kind of questions are given, like for other time points or other time instances, if we need to calculate, we can calculate it similar way. But for one or two time instance, we can calculate it using pen and paper. But for the entire time range, say for example, I need to have the response of total 500 seconds, or for 10 minutes like 600 seconds. So how we can get it? Obviously we will use MATLAB to solve it using MATLAB. So how we can code that Nigam's and Jennings method using MATLAB? Quickly go to there, and then we will come back and see other kind of numerical techniques which are actually available here. So if I open MATLAB and try to elaborate it, so let's see. Actually, I am facing some internet issue over here, so please bear with me. And am I audible now? Like I cannot use that pen thing right now. It's lagging. That's why.
You are audible, sir.
Okay, but actually I am facing the internet issue. I cannot use that pen. Like whenever I try to use that pen, it will delay, lagging. Okay. No issue, no issue. But my intention is like just understand how actually this method works. Okay, like here we will code it, and we will try to solve it using MATLAB. Okay, so Nigam Jennings method. Look for the solution. Now I think it's a little faster. Yeah, 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 yeah. Now it's good. Great. Okay. So what was the expression for the Nigam Jennings? Let's go quickly to these expressions. Here we have like we have derived it for the undamped system, and these are two expressions for the displacement at x I plus 1 and the velocity at x I plus 1. So these expressions actually we will write it over here in the MATLAB, and we will try to solve for a system, and we will actually compare these responses with Duhamel integral, because on the last class we have solved different problems using that Duhamel integral thing. So that will help us, like whether that Nigam Jennings method is working correctly or not, or for the the del t whatever we have selected for this, it is stable or not. So is my MATLAB screen is visible, right? Okay, so here this is the function file. So we are generally making, we can write the code in the script file also, but I have made a function file so that we can call it and compare it with other easily from one script. So here this function file Nigams and Jennings actually takes the input of m, k, information about the damping, information about the time array, information about the forcing function, information about your initial conditions. So if you provide this information, what this function file will give you, it will give you the displacement at any time point and the velocity at any time point. And if we get the displacement and velocity, we can easily calculate the acceleration. You just need to differentiate the velocity with respect to time, we will get the accelerations also. So how this function file will work? So first we need to define the properties, like what is the omega n. It's nothing but, because we will give the input m and k for different systems, the mass and stiffness property, damping property will be different. Now the forcing function can be different, like here we will use the El Centro earthquake for the forcing function. But for the when I showed you that PPT, there what was there, there was like a arbitrary forcing function was there, like f of t, whatever the forcing function you use here, like you can use wind load, you can use the earthquake load, you can use different kind of pulse forces, it will give you the numerical solutions of this system. So here look, first we have defined the natural parameters like omega n is nothing but square root of k by m. Omega d, that means the damped natural frequency, is nothing but omega n square root of 1 minus eta square. Now what is the time instant? It's nothing but t2 minus t1, because uh, you know I may need the response for 10 minutes, I may need the response for 15 minutes, I don't know. Like for here it's a general type of thing. Whatever time you are using, from that time step it will calculate the dt. Now nt is nothing but the length of time. You need to define it, because the responses whatever we will get with respect to the time series. Then whatever we decided, here provided the initial condition, the initial displacement is x naught, whatever you are provided. Like here if I provide the input x naught is equals to 0, that means it will start from the rest, and if I provide that xd is equals to 0, it will start from the rest position. Or I can use different kind of initial condition based on my structures. Now what I need to provide, I need to define the A, B, C, D, whatever we have derived there. So we have derived for the undamped system, but for the damped systems in nothing but the zeta and omega d quantity will be there. So A is nothing but e to the power minus eta omega n dt multiplied by eta sine omega dt divided by square root of eta. If you go to the slide, you can see that A, B, C, D expressions for the Nigams and Jennings method, or you can find it in any kind of state textbook like your Chopra or Mario Paz. Now A prime, B prime, C prime, D prime, you need to provide A prime, B prime, C prime, D prime. So look, whatever I said, like A, B, C, D, and A prime, B prime, C prime, D prime, it's actually depends on the natural properties of the system. Look, A is depends on omega n, omega d, and zeta or eta, whatever you want to say, damping. That means it's the inherent property. Different kind of structures have different kind of omega n, omega d, and zeta. Okay, same as this. Now as per the Nigam-Jennings method, my displacement at time point ti plus 1 is nothing but a multiplied by xi plus b multiplied by x dot plus c multiplied by the forcing function at I plus d multiplied by the forcing function at the next point. Okay, and xd similarly. So this function file, if you have this function file and if you provide these inputs, this will give you the responses. What responses? Xt as per the Nigam-Jennings method, and x dt, that means the velocity. That means you will have the displacement, you will have the velocity at different time point. Let's see, for a system we want to call this function file and want to solve a response. So here for the forcing function we will use the El Centro earthquake. So all of us all of we know that the El Centro earthquake. I will show you the time series of this. We are familiar with that El Centro earthquake. So here the El Centro earthquake data actually is here as a mat file or text file. So here I have a text file data. I am load it. Now T, here in the text file we have two data point. Like if I want to show you, like here, this is the earthquake data time series, time versus the ground accelerations. So we have different uh, points over, like we have thousands of data here, or for the time point, whatever time point we have, as per the time point we have. So I have loaded that data here. And then I need to define my system. Like here, mass I have taken 10 kg, k 100, and eta, that means the damping, I have taken as 5%. Now what I need to do, I need to call that Nigams and Jennings method. So what Nigams and Jennings, like here, look, this is the Nigams Jennings function file, whatever we have made. So what we need to provide here, we need to provide m, k, damping property, time, and forcing function. So forcing function here minus m into xg double dot, because it's an earthquake load. That's why for the earthquake load we have seen that effective force is nothing but minus m into xg double dot, right? When we have solved for that response due to ground acceleration, if you go back to that slides or the lecture, you can see that the effective force due to the ground acceleration is nothing but minus m into xc double dot. So, and what we need to provide? The initial conditions x0 and x dot 0. So here 0 0, we have provided 0 0. Now if I run the code, what it will provide? It will provide the displacement and velocity at different time point, and we have also compare it with uh, Duhamel integral things. So one second, the responses are coming. So for now we only run the code for Nigam Jennings. Look, yeah. So that was the ground acceleration, or we can say the load here, xg double dot, the time series of El Centro earthquake, the time series of the El Centro earthquake here. And here I have solved using Duhamel integral, because already we have talked about the Duhamel integral on the last class. So we have the Duhamel integral code ready to check whether the Nigam-Jennings code is consistent, or is there any kind of error. So for that, I have compared here with the Duhamel integral. Now you can see that both the responses actually match or align very closely. Here you can see both the responses. If I zoom this portion, look, both the responses actually align. That means my Nigam-Jennings code actually uh, gives the stabilized output for this kind of responses, and the code and function file is also correct for this case. Now if I want to solve different kind of structures, like if you have different kind of mass, different kind of initial conditions, different kind of damping properties, here you just change the values, and subsequently you can get the responses, displacement, velocity, and also the acceleration. Okay, if you get the displacement and velocity, you just need to differentiate, just use the diff command to get the accelerations also. So by this way, for any, like here times instant we have taken whatever the time or how long this earthquake load actually act on the structure, like 50 or 60 second. Yeah, for the 60 second it gives the responses. Like we can have the responses over like 100 seconds also, after the after diminishing that earthquake force, whatever is the responses, we can also get the responses likewise. Okay, so this is the Nigams and Jennings method. It's a very basics and useful method also, but for different kind of structures, we generally use go for Newmark-𝜷, or there is a popular numerical integrations method which we call ODE45, which is nothing but modified version of the Ranga-Gupta method or RK4 method. So that we also talk about. So this is the Nigam-Jennings method. It's very simple, but the assumption says it's like the force is varying linearly. That means the linear interpolation of the force is possible. Like here we talked about the arbitrary force, where arbitrary force look like this, and we consider the two time points. So for this earthquake force, look, it's very much random, like, so it will consider the linear points, and then it calculate and give me the responses. If I want to get the responses manually by pen and paper, so it will take much effort and much time. Rather, in a single click it will give the responses. So it's nothing but the xt. I can also plot the velocity, I can also plot the accelerations too. Here just you need to add this plotting commands. Okay, so I hope that Nigams and Jennings method is actually clear to you, how we can use this Nigam-Jennings method and to solve different kind of responses or different kind of dynamic responses for a given system. So if I go quickly over here, what we have done for the Nigams and Jennings method. So first, what we consider, we have considered the equilibrium conditions. That means mx double dot plus cx dot plus kx is equals to f. Then what we have done, like if we have the arbitrary forcing function over here. And if we can, that assumption says that if we um, can use that del t such that the linear interpolation can possible, then we can straight away use this method to solve different kind of responses. So what we have done over here, so we have considered that 2 point where the linear interpolation can be done. That means my del t should be small enough to get that linear interpolation thing. Then what we have done, we have defined the forcing function is nothing but the linear interpolation thing. F tau is equals to fi. Fi is nothing but the initial position. That means at t I is equals to 0, or I can say I point, and the next point is I plus 1 point. So for this 2 point, this is the forcing function. It's nothing but how I can get it. It's from the linear interpolation. Like we have already seen or know the linear interpolation things. Like if we have x1, x and x2 and corresponding y1, y and y2, we can directly linear, if fall under the linear interpolation, then we can write it down like x minus x1 divided by y minus y1 is equals to x2 minus x1 divided by y2 minus y1. Like here we have the points. Here we can say that instead of x you can use the time, and instead of y you can use the forcing function. So you can get that force at t is equals to tau. You will get this, the model of the forcing function. And from here what we have derived the response at any time instant between 0 to del t. We differentiate this equation, we get the velocity at different time instant, and we simplify the equation to get the iterative solution at I plus 1, then next iteration I plus 1 plus 1, then next iteration and next iteration and next iteration, so on, so on, so on. So here also we have solved one example where that a, b, c and d are already calculated. If not, then we need to simplify this equation, look for what is my a, what is my b, what is my c, what is my d, and from the first differential of xi plus 1 we will get a prime, b prime, c prime and d prime, like and it's nothing but it depends on the natural properties of the system. Already we have write down the expression for it here. I will provide the Nigam-Jennings codes and the function file both, so that you can apply for the other structures also as per your convenience, like here a, b, c, d and a prime, b prime, c prime, d prime, and finally the responses, right? Simple and straightforward. So we can easily solve using MATLAB. And for the Duhamel integral function file is also there. I have explained it. It's a simple thing. Like if we know the that impulse response function multiplied by your forcing function, at that point you will get the response. These things are written over there, and here it is the Duhamel integral function file. So now we will move to the next topic, like whatever we have for for the numerical integration. Um, Beyond this Nigams and Jennings method. So I hope that Nigams and Jennings method is pretty straightforward and clear. You just go through the video lecture and try to solve different problems. I will upload that MATLAB. Nanal, do you have MATLAB with you? Okay. Now we will move to another method, another popular method, which we call central difference method. Now the central difference method is also pretty straightforward, and we have some inbuilt function file for central difference method in MATLAB to solve this central difference method. So again, we start from the very basics, our equilibrium equations. So here, this is the equilibrium equation. Mx double dot plus cx dot plus kx is equals to f is nothing but the equation of motion of a damped spring mass damper system, or spring mass damper system, or here as the damper, we have designed the damper as viscous damper. So we have the spring mass damping system where F is acting. Yeah. So again, this internet actually travels me today. Uh, okay, no issue. So we need to have some patience over here. Okay. Yeah. So this is question we already know. Now at time instant I, what we can write, mx double dot I plus cxi plus kxi is equals to fi. Now here in the central difference method, what we generally do, we define that xi dot and xi double dot using the central difference. Now central difference from the numerical techniques, if you go through what is central difference, it's nothing but it says that the velocity at ith time point will depend on the velocity at xi plus 1 time point and the velocity at xi minus 1 time point. Okay, so we have defined xi dot in terms of central difference. We also have defined xi double dot with respect to the central difference. So these things actually depends on three quantities, my xi plus 1 and the previous time step xi minus 1. Now if we substitute these two in my equilibrium equation, what we will get, in terms of m, this is nothing but the x double dot, whatever we have written it in terms of the central difference method, c x dot, already we have the xi dot, so this part, and kxi is equals to f that time point. Now if we simplify it, we will get like this term, m by del t square plus c by 2 del t xi plus 1 is equals to fi minus m by del t square minus c by twice del t xi minus 1, the initial time point from the starting point and the starting point. Now here, if I want to write this equation in a simple and compact form, how I can write? It's very simple. It's k effective. That means this total part. Look at this total part. This part is known to you because the systems already, the systems you want to solve for it, it's already there. That means mc already know, the del t already know, so this is the known part. So this actually written as the k effective multiplied by the response at I plus 1 time point is nothing but the total part is written as f effective. So from this equation we can easily find out the displacement at I plus 1 point. It's nothing but k effective inverse into f effective. Okay, so if I can solve this equation, I can easily get the velocity, that is first the displacement at I plus 1 point, the velocity at I plus 1 point, and also the acceleration at I plus 1 point, right? So it's pretty straightforward. Now here is some catches are there, like when we will start like I is equals to 0, at this point my xi will become x naught. So x naught value we know, the initial displacement. Also the x dot naught, this value is also known to us. But for this quantity xi minus 1, for this quantity at t or I is equals to 0 time point, that means when we have start the iteration, that means this quantity will be x of minus 1. So how I can get this x of minus 1, and also the point is how I can get the acceleration at initial point. So the acceleration at initial point, we can get it from the pretty straightforward way. Like we just need to satisfy the equilibrium condition at I is equals to 0. So this was the equilibrium equation for us, mx double dot or here we can say for the I time point m x double dot I plus c xi dot plus kxi is equals to fi, this time point. So at t is equals to 0, that means I is equals to 0 time point, the equilibrium equation will become m x double dot 0 plus cx 0 plus kx naught is equals to f. So here, from here I can get the x naught, x double dot naught, that means the initial acceleration. Still we need to have this quantity, because for central difference method, at time instant I, if we want to consider the central difference between the ith and I plus 1 time point, so I need to have this x I minus 1 quantity at each and every time point. So how I can get this x minus 1? It's also pretty straightforward. Like here, at time instant t is equals to 0, we need to again evaluate the two quantities, like x naught, what is the value of x dot naught, and what is the value of x double dot naught. So it's nothing but I is equals to 0. Just go to the previous slide where we have defined this. Instead of I, just put 0. So we will have x1 minus x of minus 1 divided by twice delta t, and x double dot naught will become x1 minus 2x naught plus x of minus 1 divided by del t square. Now if we solve this equation, here the proof is given, it's pretty straightforward. We will have x of minus 1 is equals to x naught, that means the initial displacement, minus the time interval multiplied by the initial velocity plus del t square by 2 x dot naught. So now we have all the quantities to solve the responses. Like I have x dot, x dot naught, and x naught at t is equals to 0 time point. So here, once we have that three quantity like x dot, x double dot naught, and x of minus 1. So once we have all these quantities, we can easily calculate the response at t I plus 1, the velocity, the displacement, and the acceleration. Now here, the central difference method, the stability of the central difference method will depend on this del t value. So the stability criteria says if we have a structure which have the time period Tn, that Tn should be, for the stability criteria, the Tn should be less than equals to 1 by pi. That means typically it comes as the del t should be less than equals to 0.1 Tn. So different structures have different time period based on the natural frequency omega n. So we need to select the omega n in such a way that my time period, or within that time period, I can have minimum 10 points. That means 10 discrete time steps. Then only this method will give you the stabilized result for the solutions. So the specific requirement, like for this, when we have solved different kind of structures, like my say for example, say I have a multi-story building. Okay, say this building has 4 story. So obviously we can have different natural frequencies and natural period. So if I want to solve this structure with higher frequencies, for the higher frequencies, and for this case, if this condition, the the stability criteria or the stability condition violated, then it will give us the erroneous result. So for this structure, let's say we have different omega n, like 0.8 hertz, we have 4 hertz, we have 8 hertz, and say we have 10 hertz. So obviously, using this central difference method, first we need to understand which, or we need to first figure it out for which natural frequency and for which time period we actually able to solve this problem. uh, so obviously for 0.0 that 8 0.8 natural frequency, obviously this will give us the stable solution, and for the rest, if I want to solve using this will give some erroneous result. So for that we need to go for different kind of numerical integration methods to solve it. Typically the time step del t within 0.1 to 0.02 at the range for our 0.03 at the range, to get the stable or numerically stable solutions using this particular method. Now central difference method, to use that central difference method we have simple command on MATLAB like LSIM, linear simulation technique. Using that LSIM method we can easily solve for this. Now a few examples, let's quickly solve few examples, then we will go to the MATLAB and I will show you how using that central difference or that LSIM command we can directly get the responses, and we will compare these responses with the responses whatever we get from the Nigams and Jennings, and using the Duhamel integral techniques. So first let's solve this problem quickly, then we will go to there. So here the problem says, due to an external force the displacement xt, time history is given here. That means at time 3.05 second my displacement is 1.1 centimeter. At time 3.10 second the displacement is 0.8 centimeter. At 3.15 second, that means my del t is varying like 0.05 second, 0.05 second. Here the value is 1.4 second. So calculate the velocity and acceleration at 3.1 second using central difference method. So it's very straightforward. Like the velocity as per the central difference method, xi dot is nothing but is equals to x I plus 1, that means the next time point, minus x I minus 1 the previous time point of xi, divided by twice of delta t. So here look, we have all the values. Here delta t, how much is delta t? You can get how delta t is nothing but t of 2 minus t of 1. T of 2 minus t of 1. So here just from the table you can see the time step is nothing but 0.05 second, right? And we have the response at I plus 1. The response at xi plus 1 is nothing but 3 point at 3.14 second. Response at I minus 1 is nothing but 3.05 seconds. So at 3.10 second the velocity will be nothing but xi plus 1, that means the response at 3.15 second, which is nothing but 1.4. Response at the previous time step was 1.1, the 1.1 divided by 2 into del t. So it comes as 3 centimeter per second. Now what will be the acceleration? Acceleration as per the central difference method, x double dot I is nothing but the displacement at I plus 1 second minus 2 into displacement at the previous time step, that means xi, plus displacement at I minus 1, that means xi minus 1 divided by del t square. So all the values are given. We need to calculate at 3.10 seconds. So del t square. So here x at 3.15, that is provided as 1.4, 2x into ith point, that means 0.5 second, and 3.10 seconds. We have the ith point at 3.10 seconds, that means 2 into 0.8 plus 1.1 divided by del t is nothing but 0.5 square, and it comes as 360 centimeter per second. So please check the calculations. Okay, now instead of this table, if we provide different kind of table, like the table is little, if I extend the table little bigger, like if I put another two time instant and two responses, like say for example here, if I put 3.2 second and say 3.25 second, yeah, 360 centimeter per second, yeah. Now, no, if like if the question projected like this, instead of three values, they provide like four values, like four or five values. So how we can solve this? So 1.6. So now if they said okay, calculate the value at here. So for this thing, we need to consider that three values, and subsequently using these two formulas, we can calculate the, yeah, sorry, yeah, very, it's second square. Thank you. Yeah, it's obviously acceleration. So it must be 360 centimeter per second square, right? So now you have the idea how on pen and paper for every time step we can calculate the displacement, velocity and accelerations using the central difference technique. It's nothing but we need to have the response at this time point, previous time point and the next time point. If we have this, we can pretty straightforward calculate the responses at different time instances. Now, like here, if we have another problem, what this problem says, a dynamic force Ft is given as 15 sine 3t is acting on SDF system having mass, stiffness and damping ratio are given, like mass is given as 85 kg, stiffness is given as 45 kilonewton per meter, and damping is given as 7% respectively. Now initial displacement and velocities are given, like initial displacement is given as 1 centimeter but initial velocity is 0. We can provide any kind of initial conditions. Depend on the initial condition, the transient part will behave like based on this initial condition, and the rest will be based on the steady state response. That means due to the influence of the forcing function, whatever the force we have applied to these structures. So we have the initial conditions like this. Now what they need to what they ask to calculate, like calculate the value of x minus 1. That means at initial time point what will be the value of the previous time step in the uh, central difference method. Consider the del t is given as 0.5 seconds. So here already we have derived the expression for the x of minus 1. It's nothing but it depends on x naught, the initial velocity, minus del t of the initial initial displacement minus del t of initial velocity plus del t square by 2 initial accelerations. Now look, we have all the values which are provided here. So initial acceleration, how we can get the initial acceleration? How we can get the initial acceleration? Initial acceleration we can get after satisfying our equilibrium equation at I is equals to 0. That means mx double dot plus c x dot at 0. That means plus k x naught is nothing but my force at I is equals to 0. So here I can easily calculate what will be the x dot naught. That means the initial acceleration. So initial acceleration will be nothing but the expression will be f naught minus, like here the expression is written f naught minus c x dot naught minus k x naught by m. Now already we have the values, like what is the value of f0. So f0, obviously it will be 0 at the starting point. The initial velocity, look for the initial velocity. The initial velocity is provided as 0, that means this term will also get 0. So this term is cancel out, this term is cancel out, only we will left with this term. So minus k into initial displacement. So the initial displacement is provided as 1 centimeter, so converted into meter, because the stiffness is provided in kilonewton per meter. So here I have converted into Newton meter, Newton per meter. So multiplied by meter divided by mass is given is kg. So that comes as minus 5.29 meter per second square. Now we can easily solve this for x minus 1. It's nothing but the initial displacement minus del t of initial velocity plus del t square by 2 initial acceleration. Put all these values and recheck the calculation whether you are getting the value 0.339 centimeter or not. Can you please recheck? Like I have calculated it in a hurry conditions. Okay, so I might be wrong, but can you please cross check whether we are getting 0.339 centimeter as my that displacement at t I is equals to I is equals to 0 second. Are you there? Can you quickly calculate it? All the calculations, like we are getting it or not, so that we can fix the answers too. Okay, so we'll come back to this slide again, and now we'll try to recalculate it if there is any kind of wrong things is there. So there are any another problem from the central difference method, which says an SDF system has following properties. The mass is given, the stiffness is given. Oh, okay, okay, thank you for the confirmation. So now you know how actually on pen and paper we can solve this kind of problems. My motto is to show you how you can calculate it using pen and paper, because you ultimately for this course you need to solve it using pen and paper. Rest, for the MATLAB things, I will provide all kind of MATLAB codes and MATLAB support if you need for your future venture or your another kind of projects. I will provide them to there, and then also you can contact me, like how these files are written or how I can modify it for my own purposes. I will guide you thoroughly. But today is like I'm facing a lot of internet issue, like whenever I want to write it here, it is lagging and it is disrupting the flow of teaching. Anyway, let's solve this one. Here an SDF system has the following properties, like mass, stiffness and damping ratio. The force acting on the body and the displacement times t is given. Okay, so for t is equals to 0.1 second, the force is given 4794.27 Newton, and also the displacement is given, it's 0, initial displacement is 0. Now again 0.2 second, the force is given, force has increased, also displacement is increased. Now at t is equals to 0.3 second, we have the force. We need to calculate the value of the displacement using the central difference technique. Now here initial conditions x0 and x dot naught is given, that means my system is starting from the complete rest position, that's why the initial displacement is 0 obviously. Now in central difference method, k hat for each time instant. Okay, okay. So that they have decided the p hat. That means for each time instant, they have decided they have given a function like p hat is equals to nothing but pi minus a xi dot minus b x dot, where a and b are the parameters which actually depends on the system properties and the time interval. Now what we need to calculate? We need to calculate the displacement at t is equals to 0.3 second. So how we can calculate it? We need to calculate first that what will be that force, that Pi at t is equals to 0.3 second, and then only we can calculate the k at 0.3 seconds. And once we have that, then the response at I plus 1, that means x at 0.3 second, will be nothing but k inverse into f effective. That means f at time point 0.3 divided by k. We just need to do that. So for here, what we need to find out, we need to use that m c, we need to use another properties like omega n and c value. C, particularly c value, here the c term is over there, but in the question the damping ratio eta or zeta is given, not the damping coefficient is provided. The damping ratio and damping coefficients are different. I have already explained it on the second lecture. What do you mean by say damping ratio? What is the damping coefficient, and what is the critical damping? Critical damping means the damping required to completely diminish that vibration energy from the structure. So here all the properties are provided. What that mass is provided, stiffness is provided, so we can easily calculate the natural frequency is nothing but under root of k by m. So it comes as 22.36 rad per second. That means it's the natural circular frequency. Now critical damping, CCR, we know it's nothing but twice m omega n. So we have m mass as 120 kg, omega n 22.36 rad per second. So if we multiply it, we will get 5366.4 Newton second per meter. Please cross check this one also, like you are getting it or not. Now damping ratio is provided. We can calculate the C, because we know the damping ratio eta or zeta. We can, zeta or eta is nothing but C by C CR. So from here we can calculate the C value. So C comes as 268.32 Newton second per meter. Now easily I can calculate the effective stiffness. What will be the effective stiffness? The effective stiffness, here they have provided in terms of this expression. That means after doing that or using the central difference method, the effective stiffness comes as m by del t square plus c by twice del t. So here we have all the values, like what is the value of m, what is the value of c, and what is the value of del t. So the del t value is provided as 0.1 second. If not provided, then from the table we can easily calculate. It's nothing but T2 minus T1 will give you the del T. So the K effective comes as 1.33 multiplied by 10 to the power 4. Here, what is the value of A? Because to find out the force, we need to calculate the A. So here, in the question, instead of P, they should written it F. Okay. Let's say P and F are same things. Okay. So A comes as this, the constant A, the constant B is nothing but K minus twice M by del T square. So B comes as 36000. So can you please cross check these things? Like we are getting the values or not? So directly we can put the answers to the, if you are getting the same answer, whatever I have here, that means okay, our solution is fine and we can go for this answer to the final assignments. Or you can cross check later, or if you are doing it, just let me know. If you are doing it right now, then I can wait or I can go to the next slide. Yeah. So are you calculating, Kumar? Just cross check whether my calculations are okay or not. I just want to know. Okay.
I will do later, sir.
Okay, okay, no, just cross check them. whether you are getting it or not. If you are not getting it, just ping me or just go with that values. Okay, so whatever we have done, we have calculated k effective A and B. Now once we have A and B, we can easily calculate the force at different time point here. So the force on the next slide, they calculate the force at each time point. Fi is nothing but Pi minus Axi minus 1 minus Bxi. So A, B we have already calculated. The initial conditions already are provided. So that comes as this. Fi minus 1.06 multiplied by 10 to the power 4, that the value of A, multiplied by Xi minus 1. Xi minus 1 value already given on the table, minus 3600 Xi. So what will be the value of Xi plus 1? It's nothing but the K inverse multiplied by F effective inverse at that time point. So Fi we have already calculated using these expressions. Yeah, and K effective already we have the value 1.33 multiplied by 10 to the power 4. So what we need to find out in the questions, they have said that we need to find out the response at 0.2 seconds. So for 0.2 seconds, first we need to calculate the Fi. So F 0.2 seconds is nothing but F of 0.2 minus this X of 0.1, because I minus 1, so the previous time step, and X of I, that means 0.2. Now all the values actually have given to your table here. Look, for the 0.1 second the forcing function is given, corresponding displacement is given. For 0.2 second the forcing function is given, the displacement is also given, and for 0.3 second the forcing function and displacement both are given. So now we can easily solve for the equation, and that comes as this. Now once we have the force at 0.2 seconds, we can easily calculate the displacement at the next time point, because the displacement at xi plus 1 is nothing but fi point divided by the effective stiffness, and that comes as minus 0.25 meter. Okay, please go through the calculations and cross check them once. For 0.3 seconds, now here, if they want to they want us to calculate for the 0.4 second, follow the same procedure, you can get the value of 0.4 second. Like here for the 0.3 second they have provided the value. For the 0.4 second you can easily calculate the value using this technique. Okay, so here few MCQ type of questions may come from Nigam's Jennings and central difference method. So here let the force acting on a SDF system are Fi plus 1 and Fi for the time Ti plus 1 and Ti according to Nigam Jennings. The force at tau in between these 2 points, where del t is defined as Ti plus 1 minus Ti. So obviously the linear, if you do the linear interpolation, and in Nigam Jennings we already have discussed that the main assumption is nothing but my force varies linearly. So if we do the linear interpolation between Fi I plus 1 and in between tau, we will get Fi plus 1 minus Fi by del t into tau. Like on the very beginning we have discussed it for the model of the force here. Fi plus del Fi by del t into tau. Simple. So that will be the answer for it. Now, according to the central difference method, if we have the velocity xi dot at time ti, and if we have the constant time step del t, so the velocity at I point can be expressed as central difference techniques. It can be expressed at xi plus 1 minus xi minus 1 divided by twice del t xi. Like here, displacement and velocity we have already used it using central difference technique. Here xi dot and xi double dot, so we can easily calculate the velocity at that time point, and if we need to calculate the displacement we just need to integrate it. Now the specific requirement for stability for central difference method, I have already discussed that the del t plays the crucial role for the stability of the central difference method. So obviously The stability criteria is nothing but del T by Tn. Tn is nothing but the time period of the specific structure should be less than equals to 1 by pi. That means that del T typically varies like del T should be less than 0.1 Tn. That means within that time period, we should have 10 discrete points to get the stable numerical solution. Correct? Okay. So these are the two different numerical techniques using which numerically we can solve any responses using 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 that Nigam Jennings and central difference method. So if we want to code the central difference method, we can easily code it using these formulas, or in MATLAB we have the inbuilt option to solve it, and it calls or inbuilt function file which we call the LSIM method, linear simulation method. So using the LSIM MATLAB we will solve this system too. Like here the LSIM method is there. So now for the LSIM, if you want to go dig into it, what LSIM, how they have coded, so from where you will get it, the information, like any kind of function file. For any kind of function file, if you want to get the information about this function file, what you will write here, you just write doc LSIM. The MATLAB will provide you the complete description what that LSIM contains. Like here you will get all the information regarding the LC. If you want to go deeper into it, how it works and all these things, I suggest go through these documents. You will get the essence of how the numerical integrations will solve using that LCM method. So here we will directly use that command and to solve our system. So again we have that system, whatever we have used to solve using the doable integral things. So here look, the LCM also provide the stable solution for this system, where uh, L centro ground motion is provided as the input ports. So here also I have compared with dual integral, like to check whether my code and whether the system is stable or not, or whether I am getting the stabilized response using the LSIM command or not. So obviously I'm getting this true. So here also you can see that two responses matches closely. If I zoom it little bit, so you can see it like the two responses matches very closely using the Duhamel and using the LSIM method. Look, so we can say okay, my numerical solution is good, and we can go with the numerical solutions. Now we have two important methods. One is Newmark-𝜷 and one is Wilson-𝜷. So among them, most popular method is Newmark-𝜷 method. So within the Newmark-𝜷 method, we have two different approaches to solve it. First one is the constant average acceleration method. Constant average acceleration method. So the basic assumption of this Newmark-𝜷 constant average acceleration method is my acceleration will be constant in between two time steps. So here, if we consider two time step at ti and ti plus 1, where at ti my acceleration is xi double dot, and at ti plus 1 if my acceleration is xi plus 1 double dot, so obviously the average, that means if I want to take any point in between ti and ti plus 1, I will have the average acceleration here. So the average will be, what will be the average acceleration? The average acceleration will be half, this quantity will be nothing but half xi plus 1 double dot plus xi double dot. Yeah, again I am facing that same problem here. The solution, the expressions are given xi double dot tau. That means at any point at tau we will get the average acceleration or constant average acceleration. This, now if we have the acceleration, how we can get the velocity? You just need to integrate it. If I integrate it, I'm getting the velocity at this time point tau. Now again, if I want to integrate it further, I will get the displacement at t is equals to tau. So t is equals to tau. Now if I put tau is equals to del t, that means it will give me the velocity and displacement at t is equals to I plus 1 point. That means on the next point, because in between I and I plus 1 we have the time interval del t. So obviously at time interval t I plus 1, what will be the response? X dot I plus 1 will be, just put tau instead of tau del t in this previous expression. You will have xi dot plus del t by 2 xi double dot I plus 1 plus xi double dot. Similarly, if I integrate this, I will get the displacement at xi plus 1. It's nothing but this. Now, this is the Newmark-𝜷 constant average acceleration method. We have another thing where the acceleration is considered as that varies linearly. Now, if we have that linear variation of acceleration, so obviously we can do the interpolation between I and ti plus 1. So for this condition, if I consider at any time instant tau, what will be the acceleration value? The acceleration value will be nothing but xi plus xi double dot minus xi within bracket tau by del t. Now from here, if I want to get the velocity, just integrate it. I will get the velocity, and if I again integrate it, I will get the.
So, sir, in previous method, na, sir, you have integrated that integration. Can you elaborate, sir?
Yeah, I will provide that entire document. I have done it. Okay, like here I'm not like I am unable to write it here. Otherwise, I will show you. I will provide you the entire documents of the integrations. Okay, step by step. No issue. I will upload it. Like here, if I want to write it here, it's just lagging. It's irritating actually. Like here for this term, I will provide the entire document. Okay, no issue. I'll provide that. Here, like,
Here, sir, here, what I want to highlight, sir.
yeah,
Here, integration of x double dot I plus 1 is x dot I or something. Means here, now once we'll integrate x double dot t.
yeah,
Sorry, x double dot I plus 1. Integration of that will be x dot I plus 1. Am I right?
yeah, x dot I plus 1, right?
Okay, okay. Then I understood, sir.
Yeah. Because,
Okay, thank you, sir.
yeah, because for the next time step, if you want to find it out, so obviously you need to integrate it and you need to consider it I plus 1 time step, not at I time step, right?
Okay, sir. Okay.
I'll provide that entire document, how I will get it. Like basically that two method, and numeric has actually, combined the two in a compact form using gamma and beta term, where this two term actually leads to that stability of this solution. So here we can see that he has combined that two form and give that the solution of xi plus 1 in terms of gamma and beta, where gamma and beta is defined for two different expressions, like what will be the constant acceleration and what will be the average acceleration things. And basically that gamma and beta, that gamma is equals to half and beta lies within 1 by 6 to 1 by 4. Why? I will tell you. Because for the numeric beta method, the stability of the numeric beta method actually depends on this criteria, that del t by tn should be less than equals to 1 by 2 root 2 1 by under root of gamma minus 2 beta. So here for the average acceleration method, that means the constant average acceleration method, if we use gamma is equals to half and beta is equals to 1 by 4, that leads to del t by tn less than infinity. Just put here, you will get. That means for any value of del t, the constant average acceleration method will be stable. No matter how large your time point or del t will be, it will give you some stabilized results. But for the linear acceleration method, where we have considered that my responses varies linearly, that will only stable if and if my del t by tn less than equals to 0.005. So for linear acceleration method, we need to consider that gamma and beta value as 1.2 and 1.6, and for constant average acceleration method, if we use gamma is equals to 1 by 2 and beta is equals to 1 by 4 in this equation, f effective and k effective, and to get the responses at xi plus 1, and here the acceleration. And the second line, like here, this expression we will not directly use. What we will use here is the x double dot I plus 1, x double dot I plus 1. So from here, we can easily calculate what is my x double dot I plus 1. I can easily calculate. Once I can have all these criteria, it will be pretty straightforward, like xi plus 1 is nothing but k effective inverse into f effective. So k effective, where the k effective, if we go here, not that a complete solution is given, I will provide that complete solution how we find out that k effective. K effective is nothing but k plus gamma by del t beta c plus 1 by this quantity, and f effective will come to this. Yeah, please.
Sir, is there any questions related to this Newmark B? Um,
Beta, like you cannot solve using pen and paper, but still small kind of questions like what is the stability criteria. This slide is very important for questions like what is the stability criteria of the Newmark beta. For the average acceleration method, what will be the value of gamma and beta? For linear acceleration method, what will be the value of gamma and beta? Like this kind of problem. Here I have put one problem where you can solve using pen and paper too. Like one half sine pulse is provided here to how to get the response. I will get back to that. But this kind of questions, like short type of questions, may come from here. Like select the correct statement about Newmark beta method. The last question. Read it out. So what will be the correct answer for constant average acceleration method? Beta is taken as 1 by 4, and for linear acceleration method, the beta is taken as 1 by 6. Instead of beta, they might ask for gamma or alpha also. So this slide is important for the course purposes. This the stability criteria of the Newmark beta method. Get it? Like
okay, sir.
other
Okay,
questions
sir.
may be projected from here. Like in which method, if we have like del t, they have defined del t. Now ask, okay, within that time interval, which method of Newmark beta will be stable or will give us the stable results. Get it? So short MCQ type of questions may ask from there, but on pen and paper, these expressions cannot be solved easily, but still it can solve using that condition, like I have summarized, and you know that give the steps in other way to solve in during the or using pen and paper during the examination. It's pretty straightforward, like you just need to calculate the initial condition from the equilibrium case, and then subsequently you need to calculate a1 a2 and a3. That a1 a2 and a3, the constants you need to recall, but these things is quite impossible to recall during the examination. So I think this kind of questions, like you need to solve for t is equals to 1 point I plus 1 second, t is equals to I plus 2 second, t is equals to I plus 3 seconds, they will not ask, most likely, or they will not ask, definitely they will not ask. But MCQ and MSQ type of questions will come from here. Okay.
Okay, sir.
Okay, like if I want to code this Newmark beta, how I can code it? And these things actually done using MATLAB. Like for 10 minute simulations, how I can do it using pen and paper. It's quite tough. Like, so Newmark-𝜷, if I want to code it, what I need m. Yeah.
Sir, in exam questions will be not related to MATLAB,
No,
na?
no, 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 no,
MATLAB
no.
program.
Definitely not. Definitely not.
Okay, sir. Okay, fine. Thank you.
The questions which can be solved using pen and paper and using that on-screen calculator. They NPTEL provide you the on-screen calculator. Like, that kind of questions will be provided during the exam only. We have seen that which kind of questions from Newmark-𝜷 and central difference method and using Nigam's Jennings, this the kind of questions may ask. Like, this is very pretty straightforward question and you can solve it within seconds. Yes. So this kind of questions may ask from these questions, and the concept of beta and gamma for the Newmark-𝜷 method. Okay, so let's quickly code this Newmark-𝜷. Then we'll go to the Wilson theta, and also Wilson theta is also similar kind of technique, but there are some convergence issues like theta. The variation of theta might be within that 1.4. Normally, that we can assume this kind of questions may ask from this module. Rest bigger questions like numerically solved at t is equals to 1 plus 1 seconds, they will not ask. They will not ask, definitely. Okay, so let's quickly code this Newmark-𝜷 method. So what we need to provide here again, we need to provide the system properties, that means m, c, k, the time interval or the time series. Now the forcing function x0, that the initial condition, and x dot 0. Now we need to provide alpha and delta, that means beta and gamma value. What we now provide, we need to write that nice long expressions of k effective and f effective. So here is the expressions for k effective and f effective. Here we need to write it here, k effective and f effective. These two expressions we need to write it here. So here we can see the k effective is written here and f effective is written here. So to simplify these things, that different constants, in terms of constant, we have arranged this term. Say a naught is 1 by alpha delta t square. That means the first term here, if you go to the ppt and look it here, 1 by beta delta t square. So this quantity a1, this quantity b1, like this you can define in other type like x1, x2, x3. So as per your convenience you can code it. So here what we need to write it down, the k effective and f effective, like that nice long expressions of k and f. Once we have this k effective and f effective, what we need to find it out, we need to find it out the responses at I plus 1 second. That means these two expressions, x I plus 1 and x double dot I plus 1 from this expression. So look at here. So here x double dot t, x double dot t, from where we are getting it here, this second expressions. If you simplify this expression for x double dot I plus 1, you will get here, and x dot I plus 1, it's the written here straight away. And what is my xi plus 1, the displacement is nothing but this k effective inverse multiplied by f effective. So these three nice long expressions are written over here. Like x effective is nothing but inverse of k effective and f effective. The f effective and k effective already we have defined. Now these three response quantities, the acceleration, the velocity, and the displacement. Now if I call this function and provide the initial conditions and the system properties, this function file will give me the total response of the system. Let's say quickly solve it. Like here we have the code. Yeah, Newmark-𝜷. Now we will call the Newmark-𝜷. Again we are solving the same system, like the mass, stiffness, and damping property already we have provided here. Mass is 10 kg, stiffness is 100, and zeta is 5%. So using these properties and using the initial condition, that means the zero initial conditions, like here 0 0 initial conditions, and we are using the forcing function as the L centro ground motion. Now we are calling the Newmark-𝜷 function file, whatever we have made here. So the Newmark-𝜷 function file, if we provide this will calculate the value of xt, x dt, and x double dot t. That means the velocity, the displacement, the velocity, and the acceleration at each time point. So now call it, and you will get the response at different time instances. So if I run it, it will give me the code. Yeah. Now here I have compared with LSIM with the Newmark-𝜷. You can see there is some difference between the two responses, and this is because of like Newmark-𝜷. Here we have used that constant average acceleration method, and for the LSIM the linear, because in LSIM we have considered that the linear interpolation can be possible. Now from here and onward, if you see the forcing function, you can see it's completely random. So the linearization thing actually not work properly. Now we can see there is little variation of the responses. So in general, the Newmark-𝜷 method is more stable, and I have already shown you that from the stability criteria, if we want to use that Newmark-𝜷 average acceleration method, that means constant average acceleration method, where gamma is 1 by 2 and beta in 1 by 4, that means for any time instant we don't need to go for that linearization thing. It will solve the system and will give the stabilized responses for it. Okay, so actually this will require when you want to solve some responses using MATLAB, because by pen and paper, say for example, Nandal, you are working on which domain?
Domain in the sense, sir?
Domain in the sense like you are currently working on regarding related to any dynamic work.
Presently, actually, I am in mechanical integration, sir. Mechanical integration of launch vehicle system, sir.
Okay,
Here, my major works are related to design of mechanical integration component, their assemblies, all these things, sir.
okay.
I
So
have a little bit less knowledge and less use of dynamic, sir.
okay, okay,
Here
okay.
we are doing the bracket analysis, isolator selection for our system. So these two are the
Oh,
major activity for us, sir.
okay, 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 okay. So you need that reliability things more than your dynamics things. Structural reliability, structural
Yes, yes,
integrity.
yes,
Yeah.
yes, sir. Yes, sir.
So there is a course like structural reliability, where how that reliability index and that subsequent things are calculated. That is also there on the YouTube. You can refer this also.
Actually, if our sub-assembly we are testing FAT vibration, flight acceptance testing vibration and acoustic. During those testing, our testing facility they are using this MATLAB programming, sir.
Yeah. Do you have
Uh,
MATLAB with you?
Actually, I told you, sir, that I am not using this. That is, I have not
Yeah.
installed so far. I am in process of installation, sir.
Okay. 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 No issue. But when you are doing this course, so obviously you have some hands-on experience on MATLAB. It's very simple and
Yes.
straightforward thing. And if you require any kind of help, you just reach out to me, and I will um, help you. No issue. Just
Okay, sir. Okay,
you can use that student version also. No issue.
okay, sir. Okay, fine.
So in Newmark-𝜷 method, now if this kind of questions asked, let the displacement, velocity, and acceleration at t is equals to ti are presented at xi dot and xi double dot in Newmark's method. So at ti plus 1, it will directly depend on what? Obviously depend on the previous time step quantity. So all of the quantities xi dot and xi double dot, right? Now here the next question, like linear variation. If the linear variation is there, so what will be the displacement at ti plus 1? So that will be the expression xi dot plus del t by 2 xi double dot. This kind of small questions may ask from the Newmark-𝜷 thing. Newmark-𝜷 and Wilson theta. From Wilson theta, yeah. So But actually, it's the internet is irritating me today. Till now, it's not uh, uh, getting okay. Like still now, it's lagging. Like I'm pressing it 1 second before, and that it response comes as a 1 or 2 seconds later. Like phase lag is there. So no issue. I hope uh, uh, now you can able to solve your current week assignments, and you have that idea like which kind of questions may come from the Newmark-𝜷 and central difference and your Nigam-Jennings method. Like if we want to solve using by hand and pen and paper, this example actually will help you, and this is the steps to solve it. How? First we need to calculate the initial acceleration. From where? Initial acceleration from the equilibrium conditions at ti is equals to 0 positions. So if we have this equilibrium equation, mx double dot 0 plus cx dot 0 plus kx naught is equals to f naught or p naught. Here we can easily calculate the x double dot naught. X or u both represent your the states. So from here we can calculate it. Now we need to select the del t based on your system, whatever is provided. Then we need to calculate the coefficients a1, a2, a3. Like go to that nice long expression. So here I just break it down to three constants. If you recall these three constants, this is enough to solve the Newmark-𝜷 method on pen and paper. Now we need to calculate the k effective. K effective is nothing but a1. That means this 1 by beta delta square am plus gamma by beta delta into c plus k. That means the initial time step k. Now, once we have this, we can easily calculate the force at ti plus 1 time instant is nothing but pi plus 1 a1 uy plus a2 uy dot a3 uy double dot. Once we have this, we can easily calculate that at the next time instant, what will be my displacement ui plus 1 is nothing but k inverse of the force at that time instant. Once we have that, we can easily calculate the velocity and acceleration. The velocity and acceleration formula already given by the Newmark. Now, if we want to solve this problem, like here SDOF system is subjected to a half sine pulse, and the forcing function is given. The sine pulse is represented by this, like at 0.1 second the force is 5, at 0.2 second the force is 8.66. Like here also one thing I must mention here, like instead of giving this kind of table, they may represent the force like this. So you need to interpret the force accordingly. At t is equals to this second, the magnitude of force is this. At t equals to 2 second, the magnitude of force is this. At t equals to 5 second, the magnitude of force is this. Okay. So once, like for 0.1 second, if I want to calculate for the system, the mass is given, the time period is given, omega is given, and all are in keeps that means APS unit. Not an issue. So first we need to calculate the c, because at initially when we want to calculate the acceleration at time point I is equals to 0, we need the value of the damping coefficient. C is equals to how much C we are providing. So once we have calculated all the parameter using average acceleration method, average acceleration method means what there will be change. The average acceleration method, gamma will be 1 by 2 and beta will be 1 by 4. Please recall, gamma will be 1 by 2, and for all these cases gamma is constant actually 1 by 2. That means 0.5, and the beta value actually changes based on this stability criteria. The stability criteria here is very important. Del t by tn less than equals to 1 by 2 root 2 1 by gamma minus 2 beta. So like here now we can easily calculate u double dot not equals to 0. Del t is given as 0.1 second because the force is changing as 0.1 second. 0.2 minus 0.1 is equals to 0.1 second. Now, if we also consider the average acceleration method, so as per the average acceleration method, the beta value is 1 by 4 and gamma value is 1 by 2. And the average acceleration method is more stable. Okay, at any value of del t, we can calculate it. So first we need to calculate a1. from the nice long expression we have am, we have del t value. It's like solving the equations. The equations may look larger, but once you have all the parameter in your hand and the expressions are ready or the expressions are given, is a matter of calculation, a matter of time. So a1 is comes as 104, a2 comes as 10 point something, and a3 comes as this. Then once we have a1, we can calculate the k hat. Now once we can calculate the k hat, we can calculate the p hat on the next stage. Once we have p hat, we can calculate the u. That means the response at I plus 1. It's nothing but k inverse p I plus 1. Now once this u I plus 1 is solved, u dot I plus 1 and u double dot I plus 1 is given. So this is for 0.1 second. For the 0.1 second, all the values here, you can see all the values I have calculated. Now again, for the next time point, we need to calculate for 0.2 second. Again, repeat the process this. Again, for the 0.3 second, you need to repeat the process. Again, for 0.4 second, you need to repeat the process. So instead of using pen and paper, we can directly go for MATLAB, which actually directly gives us the values directly. Okay. Now Wilson theta, I will not explain the Wilson theta. Already your course instructor have explained it. But a few questions from here, like the value of theta. What will be the value of theta for the Wilson theta method here? These things actually important. Like normally theta is equals to 1.4, but the method is actually stable when the theta is greater than equals to 0.13. So this kind of small questions may ask from this module. Okay, so what we have done today, if we quickly summarize this. So today we talked about the numerical solutions. Numerical solutions mean we have already solved this second order differential equation mathematically. The mathematical solutions we have seen. Now numerically, like mathematically, you can solve it, but it will time consuming and it will require much effort than the numerical solution. So we have seen that different kind of numerical solutions may be there. Nigam, one of them is Nigam Jennings, where the force is considered, can be interpolated between 2 points. That means the linear interpolation of force can be possible. Now, from here, the derivation says like xi and xi dot, we just need to calculate a, b, c, d. That means the constant which actually depends on the natural parameter of the system and the forcing function at I and I plus 1. If we have all the information, we can easily calculate the displacement velocity. And if we have the velocity, just differentiate the velocity. Either you can differentiate it manually or just use the diff command, diff command in MATLAB. You will get the velocity, the acceleration from the velocity. Then we go for the central difference method, where we have seen that how to solve the responses at different time instant, and we have also seen that the stability criteria of the central difference method. Then we solved a few problems regarding this central difference method. Then we move forward the Newmark-𝜷 method, where we have seen that there might be two assumptions based on the Newmark-𝜷 method. Two assumptions of acceleration will be there. One is the constant average acceleration method. Another is the linear average acceleration method. And then combining them, Newmark has provided these two expressions for velocity and acceleration. And from here, we can easily calculate the response of a system at any time point, and subsequently the stability criteria for Newmark-𝜷 method. And we have solved different examples using MATLAB, which I will provide you. You can just explore it if you have time, and if you're interested to solve different kind of problems. Like here, you can solve different kind of responses, like uh, mm, the the tower, the launching tower. If you can define the force, you can find out the responses of the launching tower. And if you have the responses, you can do the fatigue analysis, reliability analysis of these things, and subsequent things. Okay, so for now today, we will close it here. So do you have any kind of question, you can ask me, or else I will close it.
Here, sir, actually, this MATLAB we can download from internet also, a student version.
Yeah, you can start practicing with the student person.
Okay, we can download and install, no?
Yeah, you can download and install, no issue.
Okay, sir.
You
Okay,
can
thank you.
download and install, and if you unable to do that, you just mail me. I will provide some links.
Okay,
From
sir.
where you can
Okay.
directly download.
Your email ID you have already
Yeah,
shared, no, sir?
already is there. So first
Okay.
try with the student version. This is already been there on the math work website. Okay.
Okay.
uh,
Here's a good thing. Since you are providing your assignment after the class, after your lecture, sir, whether it is possible to provide before the lecture so that we can go through what are the difference, the lecture difference, what are the different things in your assignment and what you are getting from NPTL, so that we can go through and it will be easy for us to understand better way while you are explaining these things.
yeah, no issue. Yeah, I can do it. Nice. Like you want me to add more assignments, and the assignments should be put at very beginning. So what I
Yes, yes.
generally do, yeah, what I generally do,
Uh,
like go to the concepts, like we can easily correlate to the assignments so that we can easily solve. Otherwise, we need to go back to the PPT slide, and then we need to discuss, okay, this is the expression to solve this, this is the expression for solve this. So it's better to, explain the things first, then the questions later. Like we can go back to there and we can directly correlate, okay, this is the expression which actually used to solve this, right? So
okay,
I feel that that is more convenient to
okay,
uh,
sir. Okay, I'll follow your suggestion, sir.
yeah. So that's the thing. Otherwise, what we need to do, we frequently we need to go back to the slide and look for the where is the expression. Hi, yeah, obviously if you people go through the lecture videos prior to this thing, then we can only solve the assignments. No need to explain anything. We will solve the assignments. We can add more assignments also. Okay, but generally students don't do that. Huh. So
Okay, sir. Okay.
yeah, I will try to put that assignments earlier. Like today, what I you know did is like whatever topic I have covered, I just solved the assignment first. Like here, Nigam Jennings, we have solved. We have derived the things, and then we solve it. Okay, I will try to add more assignments, and obviously I will put that in the front. But that problem will remain there. We
So
need
here, why I am telling you, sir, we will take the print, the week you are describing, and it will be easy for us to mention the details what you are explaining on that printer.
yeah.
Okay. Then in that way, what I felt, I shared with you, sir. I may be wrong
No,
also.
no, no, no. It's a great suggestion. But if all the people like all the students, if for went through that video lectures and notes, your concepts are clear, then we can easily solve. Like this question, if I directly go to these questions, like for example, this question, Nigam and Jennings method. If I want to solve it, I need to go to this expression. What is the expression for displacement and velocity as per the Nigam Jennings method? Then
Yeah,
I
this kind of yes, sir.
Yeah. So first, what I generally do, I describe this Nigam Jennings method. Here are the expressions. Now let's solve this problem. And directly we can correlate it. Okay, I will try to incorporate your suggestions too. Great.
Okay, thank you, sir.
Okay, thank you. Then